So before the presentation is ready, I understand that there are BSc and MSc students from physics and engineering. Am I right? Okay. How many people knows about the lasers and laser theory?
They know from the first day.
Yes. So, okay, I will take it into account, and I will actually give the basic theory of the lasers, and I will try to explain some possible applications of quantum dot devices. So the title of my talk is Quantum dot lasers and quantum dot semiconductor optical amplifiers. So I will give a very brief introduction in quantum dots. After this, I will explain different quantum dot laser structures and quantum dot semiconductor optical amplifiers. I will also introduce some nonlinear phenomenon in quantum dot semiconductor amplifiers, and I will show some applications of these devices. I will show the theoretical results, and so also some experimental results based on the recent publications. So why the quantum dot lasers or novel devices are required in optical communication? Because when you're talking today about the optical communications, it's completely different what was 5 or 10 years ago, because the data rate is increasing, and actually today when you are talking about the 5G applications, each user will receive more than 10 gigabit per second of downlink and uplink per user. For this reason, we need very, very high data rate optical communication systems. Also, you know about the data centers. Data centers, actually, there are firms of hundreds of thousands of servers for cloud computation, from serving the data, etc. So intra-data center communication today is approached to 100 gigabit per second, and tomorrow and in next years it will about 400 gigabit and maybe 800 gigabit, etc. Also, when you are thinking about the supercomputers, in order to allow the deep learning applications, you need the huge bandwidth between the supercomputer connections, between the chip-to-chip communication, etc. So we need the devices with low threshold current. But the low threshold current is important. If you are looking for the data centers, they are using huge amount of the power. This is the reason that Facebook, Google, Amazon, and other companies, they are building data centers in cold countries in order to save the energy. About 20% of the power is going on communication. So we have definitely reduced the power we need to operate the optical components. High-speed direct modulation and broadband modulation bandwidth is also important. You can directly modulate the laser, or you can use the external modulators. But if you can directly modulate the lasers at higher speeds, it's more simple and it's more cost effective. So we need novel devices with broad modulation bandwidth. There are also other applications for ultra-short optical pulses. we need also relatively high optical power. The noise, the issue of relative intensity noise is very important because it affects on the optical signal to noise ratio of the signal, and it is the limitation for the optical communication. So we have to reduce relative intensity noise of the lasers. As I mentioned, the cost is also important because maybe 20 years ago, the optical communication was mainly point-to-point communication from one country to another country. But right now, optical communication is in the data centers, it's in the servers, it's in the supercomputers. So the number of devices you are using in optical communication is increasing dramatically. So the cost also is an issue. And as I mentioned, the electrical power consumption also is very relevant. For these reasons, quantum dot lasers and quantum dot semiconductor optical amplifiers are very promising candidates for optical communication systems, for all optical signal processing, and I will show you some ideas how to create all optical signal processor for different purposes. So, before the quantum dots, quantum well lasers were developed, and also quantum well semiconductor optical amplifiers, and there are also different kind of devices such as multiple quantum well detectors, and etc. What is common for these devices? The size of these devices, quantum well and quantum dot devices, are about few tens of nanometers. And why? Because in typical semiconductors, the wavelength of the electron is between 7 or 70 nanometers. So if we want to confine the electrons in the device, the size of the device should be the same order. So we are talking about the devices, about the quantum wells and quantum dots, and the dimensions of these devices are about 10, 20 nanometer, so it allows us to confine the free carriers in the space. You know from different courses of semiconductor materials and maybe the courses related to the lasers, that in the bulk material, the density of states is given by this, it's proportional to the square of the energy. In quantum well, it is step function. In quantum well, it's 1 over square of E. And in quantum dot, where we have a strong confinement in all three directions, the density of states is the delta functions. This is the reason that the synonym of the quantum dot devices or quantum dots are the artificial intelligence, artificial atoms. And why? Because the structure, the dense oops, excuse me. Because the structure of energy levels of these devices depends on the material, they are depend on the size, on the temperature, on the strength of the material. So actually you can design your own atoms with certain properties. There are another and a lot of different applications of quantum devices in biology. Light emitting diode for quantum computation because quantum dots can serve as a single photon generation sources. So you can use these devices for the quantum computation, for the quantum communication, quantum cryptography, and etc. They can serve as the elements in the memory, as the photodetectors, and the lasers. Today, I will mainly focus on the application of quantum dots in laser theory, in semiconductor optical amplifiers, and actually the application I will describe, they are also related to the optical communication and all optical signal processing. So how we can fabricate quantum dots? Do you know? Any ideas? Okay. So in microelectronics, we have top-down approach. We are creating the layers. We are using the diffusion, lithography, and we can create any electronic device we are looking for. In this case, the approach is bottom-up. We are using the basic building elements, such as molecules, and actually, like the 3D printer, we are printing our devices. So two main approach is using the molecular beam epitaxy and also metalorganic vapor phase epitaxy. These are two different approaches. For the molecular beam epitaxy, we are using high vacuum chambers. This is important because we need that the scattering distance of the molecules, of the atoms, should be larger than the chamber size in order to deliver the molecules to the substrate. And in molecular organics vapor phase epitaxy, actually we are using the substrate and the chemical reaction between the substrate and the molecules. In this case, we don't need high level vacuum, but we need high pressure in order to allow to this process happen. So actually, what we will get, for example, for self-assembled quantum dots, actually we are growing one material on the other material, on the substrate. The lattice constant of the substrate is different from the quantum dot material lattice constant, and in certain conditions for the certain width of the material will collapse in sphere in other form, and we will get the islands of this material on the substrate. These islands are organizing the quantum dots. The quantum dots are different in size. It's difficult to manage the size of quantum dot. This leads to the inhomogeneous broadening of the device, and devices are operating in wide range of wavelengths. So if we are using indium arsenide or gallium arsenide materials, the wavelengths we will get from this kind of devices are in the infrared regime. It's widely used in optical communication with other materials, indium gallium nitride quantum dots and gallium nitride. They have potential to cover the complete visible range for different applications and for 2 and 6 semiconductor systems, the luminescence is in the range of about 500, 600 nanometer. So we can cover almost all interesting area of wavelengths using different materials for quantum dot devices. How we can reduce the threshold current? Actually, the first works on reduction of the threshold current was done 60 years ago, and this leads to the development to the double hetero structures. And you can see the progress over the time, and you can see the reduction of the threshold current using the quantum dots. The reason that we can achieve such lower threshold currents is the high confinement properties of quantum dots. Electrons and holes are highly confined in the quantum dot, so once electron is catched by the quantum dots and we have a transition, we will get a photon, so we can significantly reduce the threshold current of these devices. Actually, what is the double heterostructure? In double heterostructure, we have, for example, here we have gallium arsenide, and we have p-n junction. We have some amount of aluminum. Actually, it allows us to manage the gap of the semiconductor. So in this case of the double heterojunction, you can see that electron cannot escape from this area. So if it is the active area for the laser, and we are using the current in order to create the inverse population, and most electron and holes will concentrate in this area, we have high recombination rates in this area. This means that we can achieve higher power, optical power, with the same current. Also, we can design the refractive index in such a way that we will create the waveguide in order to get the photon illumination in certain direction. So this is the example of the structure of quantum dot, or quantum dot in a semiconductor laser. Actually, what we have the p-n junction. This is the active region. This is the zoom in the active region. You have the islands of quantum dots, and actually we are using several layers of quantum dots. The reason that we want to get high optical power, so in this way we are increasing the number of the quantum dots in the active area. So the structure is the same, almost the same as in bulk semiconductor laser, but the active region is different. Active region includes the quantum dots as it is shown in the picture. Okay, this is actually the same image of the quantum dot. This is the active area. In the active area there are a lot of quantum dots as it is shown here. Before I am going to describe the theoretical models of quantum dots, I want to describe the basic phenomena of light-material interaction. Once we will understand these basic phenomena, we can relatively easily understand the operational principles of the laser. So what we have, I will consider two-level system. We have the ground state, E1, and we have the excited, unstable state, E2. And we have a photon with the energy, hν, and hν is exactly equals to the energy of the gap between these levels. So first process we have, and we understand it, it's absorption. Because if we have the atoms or electrons at this state, and we have enough energy to transmit the electron from the ground state to the excited state, what we will get, the photon will be absorbed, and we will get the electron at the excited state. The second process is also very logical, because we have the electron at the excited state. This is not comfortable for the system. System is looking for the low energy. So after some time, the electron will go back to the ground state. This process is called spontaneous emission. And we have another process called the stimulated emission. What is stimulated emission? When we have electron at the excited state, and we have the photon with the proper energy, this photon can lead for the transition of the electron from the higher level to the lower level, and in this case we will get two photons with exactly the same energy and with exactly the same phase. So actually this process, this process, the stimulated emission, is very important in the theory of the laser. What is the laser? Light amplification by stimulated emission of radiation. Okay? Do you know this guy? Okay, so he was the first who described the phenomena or the process of the stimulated emission. So once we understand how the photons are interacting with the material, now we want to create the model for the laser. There are two ways to do it. The first way is to begin from the Maxwell equation to get the wave equation in the waveguide, describe the dynamics of the electrons in the active region. This is the second equation. And those two equations are coupled by epsilon. But it is a long way. I have not enough time. So I will introduce the second way. The second way is phenomenological based, because if we understand the process in the laser, we can develop the rate equations for photons and the rate equations for electrons. So what we have? As I mentioned, we have absorption, we have stimulated emission, and we have spontaneous emission. So if I want to describe the dynamics on photons in the laser, I have take into account all these processes. This one is proportional to n, to the concentration of the electrons, and this is the lifetime of the electrons. So this term is spontaneous emission. Why the sign is plus? Because due to the spontaneous emission, the concentration of photons will be increased. What is this term? It's proportional to the concentration of the photons and the photon lifetime, and this term is with the sign minus. So due to this process, the concentration of photons will decrease. So it should be absorption, because when photon is absorbed, it creates electron at the excited side. And what is the first term? The first term should be the stimulated emission. Why? Because it's proportional to n and it's proportional to p. So it's proportional to the probability that photon will meet the electron at the excited state, and the result of the stimulated emission, we will get 2 photons. And this term also with sign plus. Here we have n minus n0. What is the reason for this? The reason for this that when we are making the real laser, the materials are not perfect. There are a lot of losses in the material, and we need some concentration above the certain amount of free electrons in order to make the region active, in order to get amplification of the light. Also, we have here another term which describes other losses on the mirrors, because for the laser we need some cavity. It can be Fabry-Perot, it can be a DBR, DFB, but we have a lot of losses in the device. So this is the first equation. And the second equation, excuse me, what is gamma in this equation? Gamma is the portion of photons which are confined in the active region. Because if I have a waveguide and I have the propagation of electromagnetic field in the waveguide, not all amount of energy will stay in the waveguide. The part of the energy will go outside. So gamma is so-called confinement factor, and it describes the amount of electromagnetic energy which is guided in the device. The second equation is the equation. Excuse me?
15 minutes more.
Okay. The second equation is the equation for the electrons. Here we have here we have the current, also stimulated emission, also the spontaneous emission, and other terms which are called bimolecular and Auger recombination. The other recombination process takes place for the high concentration. Also, we have described the phase behavior of the laser, because phase behavior of the laser is very important. This factor is called line width enhancement factor. When you are directly modulating the laser, you are changing the concentration of free electrons. When you are changing the concentration of the free electrons, you are changing the imaginary and real part of the refractive index. So according to the very well-known relation, there are some relation between the imaginary part and between the real part, and this is called line width enhancement factor. If you have very large line width enhancement factor, you have very fast changes in the phase. This phenomena called chirp signals, and when you are directly modulating the lasers, if you have a huge amount of the chirp, it will lead to the increasing of the bandwidth. It like the phase, it like the frequency modulation, it will lead to the huge bandwidth of the transmitting signal. So if you are using the fibers, dispersive media, it can be very, very problematic. So once we understand the basic of the laser operation, we can move to the quantum dot laser. In quantum dot laser, actually we have some wetting layer. It serves as a reservoir for the free electrons. In the conduction band, we have two levels. One of them is the ground state. The second is excited state. And we have also two levels in the valence band. So if we want this to describe the dynamics, the behavior of such a laser, we have wrote down the rate equation for each layer, taking into account all possible transition between the levels, including the stimulated, spontaneous, emission, and absorption. So these are the rate equation from the concentration of electrons in the reservoir, in the wetting layers, for the excited state, for the ground states. We are not taking the whole dynamic into account due the difference between the dynamics and between the effective mass of electrons and holes. We have also the equation for the optical power. This term actually is the stimulated emission. This one is a spontaneous emission. It's absorption, and this is the spontaneous emission. And we have all these time parameters, which is actually the escape time from the one state to the other state, and the capture time from the higher levels to the lower levels. And we have also the equation for the phase. Delta omega here is actually describes the fast deviations from the central wavelength of the lasers due to the dynamic of each level. You cannot solve these equations analytically. The way to do it, you can use the MATLAB, you can use COMSOL or other numerical tools, because the equations are strongly nonlinear. It is impossible to solve them numerically, analytically. There are other structures of the quantum dot lasers, so-called quantum dot in well laser. Quantum dot is placed in the strained quantum well. In this case, the dynamic equations, the rate equations are very, very complex. You have to take into account the whole dynamic. Actually, rho E and rho H are the quantum electron and hole occupation probabilities. At the in the quantum dots, V and VH are the electron and hole densities in quantum wells. And you have also nonlinear scattering rates. So this set of rate equations is very complicated. And sometimes you can get also the chaotic behavior due to the nonlinearities in the laser. So it's a very rich device by means of the properties and by means of performance. What is actually quantum semiconductor optical amplifier, and especially quantum dot based semiconductor optical amplifier, is very similar to the laser. The difference that in this case we have not cavity, because we have the input to the device, low power signal is launched to the device, and actually after the amplification you get the amplified signal. The rate equations for the quantum dot SOA are very similar to those for the quantum dot lasers. I will not go in details, but the presentation is published, so you can take your time, and when you will find it interesting for you, you can go to these equations. So I want to go to the applications because the time is short. Here you can see the experimental results. It's a Fujitsu device, the quantum dot device. You can see here the dependence of the optical power on the injection current. This slope is very important. This one is called laser slope efficiency. Actually, if you have high slope efficiency, it's better because it gives you the understanding how much electrical power can be converted to the optical power. And in comparison to the quantum well, you can see that this characteristic is also very linear. Linearity of this characterization is important for the direct modulated lasers, especially when you are using analog signals. And you can see also the temperature sensitivity of, and comparison between the temperature sensitivity of a quantum dot and quantum well devices. It's quantum dot at 20 degrees of Celsius, and this is the quantum well. And you can see that eye diagram. Do you understand what is the eye diagram? Are you familiar with this one? No? No. So actually, when you are transmitting a so-called on-off king. On-off king is the modulation form when you are transmitting 0, a low optical level, and 1 for the high optical level. In this case, you can transmit the information. So in order to check the performance of the system, you are just accumulating these symbols. And in the case that you have the noise or dynamical properties of the device are poor, this is called eye diagram. This eye will be very closed. Okay? So if the eye is open, the situation is good. If the eye is closed, that means that we have a lot of amount of the noise. So 0 is not a certain level. You have a lot of fluctuation near the zero, a lot of fluctuation of a high level. Also, you can see this is the rise time and this is the fall time. So if laser has not enough bandwidth, actually it acts as the low pass filter. So if I am trying to modulate the laser beyond the 3 dB bandwidth, actually the rise time and fall time will be very large. So it will lead to the closing to the eye. So this one is very informative. You can study a lot about the performance of the system. So as you can see, that the performances, temperature stability of quantum dot device is very important. And why so important, the temperature stability? I mentioned the 5G systems. If you are talking about the data centers, all optical devices are inside the data centers and temperature is very well controlled. But you are talking about the 5G systems, they are distributed. They are everywhere. You cannot control the temperature, but you need the same performance in very huge range of temperature. So this is very important. Okay, actually semiconductor optical amplifiers, 3 minutes, okay, I will, are important due to the very high nonlinear phenomena, so-called cross-gain modulation and cross-phase modulation. What is the cross-gain and cross-phase modulation? If I am using two wavelengths and I am launching them to the device, they are comparing. You have a high power and I have a low power. Actually, I am 0, okay? No photons at my wavelengths. You will get all the gain of the device. But if I also have a high power, I will take some energy from you. So your gain will be less. So in this case, there is a crosstalk between the gains of the devices. This is called cross-gain phenomena. And also I will affect on your phase because I am changing the concentration of the free electrons. I am changing the refractive index, so you will feel this change. Also, one more important phenomena is four-way mixing for high nonlinear, third nonlinearities in the semiconductor optical amplifier. You can all these phenomena also in optical fiber. But in semiconductor optical amplifier, which is very small device, is less than 1 centimeter, you have the huge cross-gain and cross-phase phenomena. You can use these phenomena for the optical signal processing. Let's try to understand it. I have Mach-Zehnder interferometer, I have 2 arms, and I have theoretically the exactly same quantum dots. So I will use the clock stream or continuous wavelength. It does not make matter. And I will use the stream A and stream B. A and B can be the same. They can be different. If the Mach-Zehnder interferometer is balanced, I will get, in the case that A is equal to 0 and B equal to 0, the interferometer will stay balanced. I will get 0. So 0, 0 leads to 0. 1 and 1, the interferometer still will be balanced. So 1 and 1 leads to 0. Just in the case 1 and 0 and 1, I will get 1. It is the XOR operation. And I can achieve 115, 160 gigabit per second operation of this optical logical gate. So I can make all optical signal processing. I can build logic gates. So there are some theoretical results. This is the implementation of this all-optical signal processing for the optical memory. Sometimes I need the optical buffers in the data center. Two packets are deriving in the same time. I have packet collision. How can I mitigate the packet collision? If I have the optical memory, I can send one of the packets to this memory, and when the path will free, I can transmit it. So this is also one of the applications. You can see the theoretical results, 100 gigabit optical memory, direct modulation of lasers for 5G systems. You can see here the carrier of the radio signal, the microwave signal, is 60 gigahertz. So using the external injection to the laser, I can improve the dynamic properties, and actually I can get the synchronized dynamics in the quantum dot, and I can achieve the high performance of radio over fiber system, transmitting the information at the central carrier frequency of 60 gigahertz. It's very important for 5G. And this actually improvement of the error vector magnitude using the external illumination. Okay, I will skip this one because I understand that we have not enough time. Experimental work for May mixing, for the wavelength conversion from lower frequencies to higher frequencies in quantum dot semiconductor amplifiers. Thank you.
Don't do this. In Britain means, very bad things. So, any questions? Any questions? I think that they are tired. They're here, since the morning. I have a question. Actually, I would like your comment because I would like to combine this question with the question that I have to Jim. So, lasing, in order to observe lasing, a lot of people, they have stated that, they have seen lasing and stuff like this. So, it's a very, very big issue to state that you can see lasing. So, the criteria is, of course, the existence of the threshold, the landwidth reduction, but also we should mention something about the coherence length and the coherence time. So, are you agree, since you talked to us about the laser fundamental?
Yeah, actually, in quantum dots, you can achieve very low line with enhancement factor. It should be close to zero due to the structure of the device. But you can also design the line with enhancement factor according to your needs, because in some cases, you want to perturb the signal in order to mitigate the dispersion at the transmission. Mm-hmm. So it's manageable. You can begin from zero and manage it in your own way.
Yeah. In your case?
No, I agree. In fact, I don't know if the perfect approach is like what the nature journals do now, which is now they have a checklist. Exactly. But I'm glad there needs to be something like that, because otherwise it's too easy to have to see one, see your light curve, have a nonlinear kink and things.
Yeah. So no one trusts the kink because the kink also exists with lens. Yeah. So another thing is that the next step is like to see the landwidth. But they have also they would like to calculate the coherence length and the coherence time. Did you measure this in your system?
We haven't directly measured the coherence.
You can go through the landwidth to calculate the coherence time, and then
Exactly. So we do that, and then we also look for, we actually have a beam coming out of our structure, so we can look at the coherence spatially.
Right. Because it's like the solar cell now. In the solar cell, a lot of people they support that they have efficiency is very high, but of course this should take standard measures. The same happens also with the laser systems. A lot of people they have said that especially in these small systems that they can see lasers.
No, exactly. We're dealing with the nonlinear system already, right? So we can fool ourselves easily.
All right. Thank you.
And also you mentioned the very short pulses in your system, and I think that the repetition time was about 80 megahertz.
In ours Ours is CW.
Yours is CW. So using the quantum dots, you can create the pulse lasers with variable repetition rate till 50, 80 gigahertz. So it's very interesting.
Since it is CW, so I was expecting if you measure the continental length to be, several meters. Depending on the wavelength.
Yeah.
So,
Yeah.
how is it? Thank you very much again. Thanks, Ben. Yosef. Thank you.